Hi there! Welcome to our new episode of The Logic of Risk. Thank you all for the growing number of listeners and for the messages and the suggestions you send me almost every day through my personal website and social media. I would like to remind you about the website thelogicofrisk.com, where you can find additional materials, when available, and useful references if you wish to delve deeper. Okay, let's start. In today's episode, we continue examining the concept and tool of probability, which, as we know, is essential for us in order to quantify and manage risk, and, at least partially, also uncertainty. In recent episodes, we discussed some general considerations about probability, noting the existence of multiple schools of thought in the field of probability. Some of these schools are objectivist, meaning they view probability as something objective that exists independently of the human mind, an impartial entity potentially measurable with precision using the right instruments, and comparable to physical concepts like mass, force, and velocity. For Mises, frequentism falls into the objectivist universe. It has been revisited and reshaped by several scholars, including Donald Gillies, whose An Objective Theory of Probability, written in the 70s, is a fundamental text for anyone wanting to explore objectivism in more detail. However, Gillies' perspective goes beyond simply rearranging von Mises' ideas. Indeed, Gillies can be considered something of a bridge builder between frequentism and another objectivist school of thought, namely the propensity school, whose major exponents are Charles Peirce and Karl Popper. Chronologically, Peirce came first, in the 19th century. His aim was to reconcile the pragmatism of which he was one of the leading minds with the notions of potentiality and contingency. But it was Karl Popper who, many years later, and we might say independently, made the propensity school widely known. On the other side of the spectrum, we find subjectivist schools. For these schools, probability is inseparable from the subject. It is not an object that exists on its own, but rather something intertwined with the ideas, the concepts, the qualities, and limits of whoever uses it. Within the subjectivist world, we have, among others, the Bayesian viewpoint, the epistemic perspective, and the credibility approach. Major figures in this field include Frank Ramsey, who died at just 27 but made a fundamental contribution to probability theory, Leonard Savage, described by Milton Friedman as one of the few people worthy of the title genius, and Percy Diaconis, who, besides being a great mathematician, is also a professional magician. There are many more, such as Hans Bühlmann, Richard Jeffrey, and of course, my dear Bruno De Finetti, a great Italian probabilist to whom I would like to devote an episode sooner or later. Outside of objectivism and subjectivism, we find certain schools, such as the classical one, which can be seen as the forerunner or root of all subsequent developments and has traits of both major worldviews. We also find the axiomatic school and the logicist school. The axiomatic approach can be seen as a way to dodge the debate, taking refuge in a somewhat metaphysical view of probability. A great representative of this school is the giant Andrei Kolmogorov. The axiomatic perspective is the standard approach to teaching probability, especially in mathematics and physics. Yet, it is also increasingly used in economics and actuarial science, where, in the past, frequentism prevailed. On the one hand, introducing the axiomatic theory as the first approach to probability is a sound choice, because it allows students to study probability as a branch of mathematics, applying the knowledge they have already acquired, without worrying too much about deeper epistemological issues. On the other hand, it is a choice that can lead many students to think that probability is only that. They may then collide with real-world situations where you have to get your hands dirty, and where certain elegant theoretical properties do not hold. The axiomatic construction, which works beautifully in theory, turns out to be inadequate for dealing with the many practical problems one encounters when working with data. Even something as basic as distinguishing between single events and large-scale random phenomena is not easy to handle from a strictly axiomatic perspective. We discussed these two types of phenomena in the previous episodes, which I encourage you to listen to if you haven't yet. It will soon come in handy. The logicist school, on the other hand, forms something of a bridge between the subjectivist and the objectivist perspectives, or at least, that is how I see it, since I view logicism as an attempt to unite these two words. However, some scholars claim that logicism is a kind of subjectivism, while others say the logicist view is actually objectivist. In reading works by the great logicists Keynes, Wittgenstein, Weissmann, Reichenbach, or Keyborg, I personally find that seeing it as a bridge is the most appropriate stance. In logicism, probability is viewed as the degree of reliability of a given proposition, ranging from 0, false, to 1, true. According to Friedrich Waismann, no concept, especially one of an empirical nature, is fully defined and permanent. Rather, each concept is subject to continuous clarifications and revisions. It is as though each concept were surrounded by a membrane that encloses it, giving it shape, but that membrane is porous, allowing meanings to flow in and out. As an example, consider the concept of money and how it has been challenged by cryptocurrencies, such as Bitcoin. Indeed, among economists, the discussion is still ongoing. Some do not consider cryptocurrencies to be money, for instance, citing their volatility, which calls into question their use as a unit of account, while others argue they are. Or consider friendship and how its definition has changed in the era of social networks. Who do you call a friend? Clearly, probability is a porous concept as well. But let's rewind a bit and proceed step by step. In the last episode, we started with the classical definition of probability. As mentioned, it is not very useful from a practical standpoint. It only applies to highly idealized situations and certain gambling scenarios. Nonetheless, it deserves discussion both for its historical importance, it was the first formalization of the concept of probability, and because other schools, like the frequentist one, arose to address the shortcomings of the classical definition. We said that, in the classical view, the probability of an event is nothing but the ratio of the number of favorable outcomes to the total number of possible outcomes, under the assumption, citing Pierre-Simon Laplace, that nothing leads us to believe that any one of these outcomes should occur more frequently than the others, which makes them all equally possible in our eyes. Hence, probability is the result of a simple division. The numerator is the number of times the event of interest happens, and the denominator is the total number of possible outcomes from the random phenomenon in question. So, once again, if we consider a six-sided die roll as our random phenomenon, we have a total of six possible outcomes, 1 through 6. That will be our denominator. The numerator changes based on the event we want to study. If I'm interested in the probability of rolling a 5, there is only one favorable outcome out of 6, so the probability is 1 over 6. If I want the probability of rolling an even number, there are three favorable outcomes, 2, 4, and 6. So the numerator is 3 and the denominator is still 6. The probability is therefore 3 over 6, that is 0.5. And if I want the probability of rolling a number strictly less than 3, the favorable outcomes are just 1 and 2, so that is 2 out of 6, or 1/3. If I say less than or equal to 3, then we have 1, 2, and 3, three favorable outcomes, so 3 out of 6, and so on. By counting the favorable outcomes, summing them, and dividing by the total number of possible outcomes, we are implicitly considering each possible outcome, or elementary event to use the term from the last episode, as equally likely. We are not giving them different weights. In the role of a fair six-sided die, the probability of each elementary event rolling a specific side is indeed 1 over 6. As we noted last time, and also in the words of Pierre-Simon Laplace that we have just cited, the assumption of equiprobability is linked to the principle of indifference, according to which we should never consider certain outcomes more likely unless there is a strong contrary evidence. Simply reading the classical definition reveals its main limitations, though its historical merits and its impetus for later developments are undeniable. First, in order to use the classical definition, we must be able to precisely count both the favorable outcomes and all possible outcomes. This implies that the number of outcomes must be finite. That is a major restriction. Indeed, while the classical definition easily handles the probability of rolling a 6 with a single die, or even the probability of rolling 4 3 times when rolling 10 dice, it becomes significantly more complicated if, for example, we want to determine how many die rolls we need on average before we get a 6. The classical definition doesn't tell us what to do when the number of outcomes is potentially infinite. Unfortunately for us, especially in risk management, there are only a few situations in which the outcomes of a random phenomenon are finite and easily countable. As mentioned, the classical definition can work in some simple gambling contests, but even modest modifications of the game reveal its limitations. Under the classical definition, we are unable to say what the probability is that the price of a company stock will rise by X% or more tomorrow, or the probability that a bridge will be damaged by a severe storm. Moreover, the classical definition of probability suffers from what probabilists call the circularity problem. By defining probability as the ratio of favorable to possible outcomes, we are assuming that these outcomes are equiprobable, as we said. In other words, we are relying on the idea of probability, equiprobability, to define probability, as when we say that a coin is fair, but end up defining fair to mean that heads and tails happen with equal probability. Many scholars have tried to solve the circularity problem, for instance by working on the notion of symmetry. A die is indeed a symmetrical object, but no solution has been fully satisfactory, especially since asymmetry is very common and, if you like, more interesting to analyze. One of the best-known solutions to the problems of the classical definition is offered by the frequentist school, an example of the objectivist view of probability. If you have studied some probability, especially in social science departments like economics, there is a good chance that frequentism is what you have encountered. Prominent names in frequentism include John Venn, famous for Venn diagrams, Ronald Fisher, one of the fathers of modern statistics, Jerzy Neyman and Egon Pearsons, both giants of statistics, and Richard von Mises, a polymath not to be confused with his brother Ludwig von Mises, the influential economist. In his treatise on probability, the logicist John Maynard Keynes suggests that one of the first frequentists in history was Aristotle. Other historically important figures in frequentism include Bernoulli, Gauss, and Laplace. We already mentioned Bernoulli and Laplace as among the founders of the classical definition of probability, but it is undeniable that in some of their results they more or less implicitly used a frequentist viewpoint as well. Two absolutely pivotal texts for the frequentist school are The Logic of Chance by John Venn, published in 1866, and Wahrscheinlichkeit, Statistik und Wahrheit, Probability, Statistics and Truth, written by Richard von Mises. The latter was first published in 1928 and revised in 1936. It is a clear, accessible essay, rich with interesting examples and almost devoid of formulas. Reading from the original text, von Mises' goal is to, quote, show how, starting from statistical observations and applying to them a clear and exact concept of probability, we can arrive at conclusions which are reliable and true, and in practical life just as useful as those obtained by any other exact science. Unquote. It is definitely an objectivist point of view. For frequentists, the probability of an event corresponds to the relative frequency of that event over time, or, better yet, the theoretical value of that relative frequency. The word frequentism derives precisely from this focus on frequency. The central idea is that when analyzing a random phenomenon, we record and study its manifestations over time, and we define probability as the ratio between the number of times the event of interest happens and the total number of observed outcomes of that random phenomenon over time. And since time can possibly go to infinity, we introduce the concept of limit. But I have talked enough for today, so I will leave you with this cliffhanger. See you next week. Have a pen and paper at hand if you like. It is not strictly necessary, but it might be useful. Ciao ciao!